Have you ever heard of fractals? Fractals are fascinating mathematical objects that are not only beautiful but also useful in a wide range of fields, from computer graphics to physics and biology. What are fractals? A fractal is a mathematical object that exhibits self-similarity at different scales. In other words, if you zoom in on a fractal, you will see the same pattern repeated over and over again, at finer and finer levels of detail. Fractals can be found in nature, from the branching patterns of trees and rivers to the shapes of clouds and mountains. They can also be created using simple mathematical formulas and algorithms. To understand fractals, let's start with the story of the English coastline. The story of the British coastline is a classic example of how the concept of fractals can be used to understand complex natural phenomena. It all began in the 1960s, when a British mathematician named Benoit Mandelbrot started exploring the idea of fractals. One of the first things that Mandelbrot looked at was the length of the British coastline. To his surprise, he found that the length of the coastline varied depending on the scale at which it was measured. For example, if you measure the length of the coastline with a ruler that is 1 kilometer long, you will get a different length than if you measure it with a ruler that is 100 meters long. This is because the coastline is not a smooth, straight line. It is full of twists and turns, inlets and bays, and other irregularities. Mandelbrot realized that the coastline of Britain, and many other natural features, had a property known as self-similarity. This means that as you zoom in on the coastline, you see the same patterns repeated over and over again. For example, a small section of coastline might have the same shape and features as a larger section of coastline. Using this idea of self-similarity, Mandelbrot was able to develop a mathematical formula to describe the fractal nature of the coastline. He called this formula the fractal dimension, which is a measure of how much space a fractal object occupies. We will discuss this concept in a few slides. The fractal dimension of the coastline was found to be greater than 1 but less than 2, which means that the coastline has more length than a straight line but less than a two-dimensional area. This discovery had far-reaching implications for the study of natural phenomena. It showed that many natural features have a fractal nature, which means that they cannot be fully described using traditional geometry. Instead, they require a new type of mathematics that takes into account the complexity and irregularity of natural shapes. Another example is the Menger sponge, which we are asked to implement in this milestone. The Menger sponge is a three-dimensional fractal object that was first described by mathematician Carl Menger in 1926. It is a cube-shaped sponge that is constructed by repeatedly removing smaller cubes from its interior. Specifically, the Menger sponge is created by taking a cube and dividing each face into 9 equal squares, with the central square removed. Then, this process is repeated on the remaining smaller cubes, and so on, ad infinitum. The Menger sponge has also been the subject of much research in mathematics and computer graphics. It has been used as a benchmark for testing the performance of various algorithms, as well as a tool for studying the properties of fractals and their applications in science and engineering. One of the key properties of fractals is their self-similarity, which means that they look the same at different scales. This makes them difficult to measure using traditional methods, such as length or area. Instead, mathematicians use the concept of fractal dimension to describe the size and complexity of fractals. There are several methods for determining the fractal dimension of a shape, but one common approach is the Hausdorff dimension. This involves covering the fractal with a set of smaller and smaller boxes, or balls, and counting how many boxes or balls are needed to cover the entire fractal. The fractal dimension is then calculated as the limit of the logarithm of the number of boxes or balls needed to cover the fractal divided by the logarithm of the size of the boxes or balls as they become smaller and smaller. Another approach to determining fractal dimension is the self-similarity dimension. This involves comparing the fractal to itself at different scales and measuring how the size of the fractal changes as the scale changes. The self-similarity dimension is then calculated as the logarithm of the ratio of the size of the fractal at two different scales divided by the logarithm of the ratio of the two scales. The Menger sponge has a fractional dimension that is greater than 2 but less than 3. This means that it takes up more space than a solid object but less space than a three-dimensional object. Fractals are not only beautiful and intriguing, but they also have practical applications in a variety of fields. One of the most well-known applications of fractals is in computer graphics, where they are used to create realistic and detailed images of natural objects like mountains and clouds. Fractals are also used in signal processing to compress and decompress digital images and sounds. In finance, fractals are used to analyze complex data sets and identify patterns that can help investors make better decisions. For example, the famous Mandelbrot set, named after the mathematician Benoit Mandelbrot who discovered it, has been used to model stock market prices and predict market volatility. Fractal geometry is also used in the study of natural phenomena, such as the branching patterns of trees, the shapes of coastlines, and the growth of coral reefs. By applying fractal analysis to these natural objects, scientists can gain insights into the underlying processes that create these complex structures. In medicine, fractals are used to analyze and model complex biological systems, such as the human circulatory system and the branching patterns of neurons in the brain. This can help doctors and researchers better understand these systems and develop new treatments for diseases. In conclusion, fractals are fascinating mathematical objects that exhibit self-similarity at different scales. The Menger sponge is an example of a fractal that is easy to understand and visualize, but there are many other types of fractals that are more complex and abstract. The concept of self-similarity and fractal dimension has many applications in science, technology, and art, and it is a testament to the beauty and elegance of mathematics.